Hello everyone. So this week we will talk about organic chemistry, the history of organic chemistry, and we will focus in the period between around the 18th and 19th century, at the beginning of the 19th century. So last session we were talking about Berzelius, who was definitely one of the most influential chemists in history of that period. And until today, we use many of the terms that he gave to different chemical processes. And then during this session, we will see some of his contributions. And we will see also that he did uh, great contributions, but also because of his very strong character, he rejected or affected the development of science for some people like Auguste Laurent. So this also shows something about his character and like a person, not just like a chemist. So let's start. Talk about the history of organic chemistry. We should talk a little bit about the history of humanity itself, because from practical experience, societies and people or the mankind could divide substances into two different classes of substances. One, which was the combustible group of materials, and the second, the non-combustible. We know that the principal fuels in early times were mainly wood, fat, and oils, and all these products they belong to products that come from the plant world or the animal world, while all the non-combustible materials they come from mineral world. And we know already, and we discussed a lot about how was the influence of this mineral knowledge to the development of chemistry and all the discoveries they were doing since ancient times for the smelting of minerals. However, to talk about organic chemistry, we should focus on the living world. And for the scientists of the 18th century, uh, they could already make some differences between these two classes. Like, for example, they found that substances from the non-living world, they were much more stable. So they could resist some harsh treatments that they were doing, for example, for the smelting or for when they were heating, for example, water, they could evaporate it and recover it in condensation, and the product was keeping the same properties like it was before. But if you try to apply those harsh treatments to organic compounds, then you easily see that the compound is not what you can recover after the treatment, if you can recover any. It has totally different properties. So one of the divisions that could be seen already in the 18th century was about this stability differences between mineral and organic compounds. Uh, Another important difference that could be uh, noticed by chemists in the 18th and 19th century was that some of the inorganic compounds can be produced from the organic ones, but not the other way. Like, for example, when you are doing the combustion of wood or some organic compounds, then at the end of the process, you can recover ashes that they resemble the properties and the composition of inorganic compounds. But it was not possible at the time to build organic substances from inorganic ones. Because of this clear difference, or this important difference, uh, and because of something that still persists today, life itself it was involved with certain mysticism. And about this, it was developed a theory or a concept called vitalism that stated that organic compounds to be formed, uh, first of all, it was required to be produced by a living organism. And the characteristic of the living organism is that it had a vital force that was responsible for this capacity of operating with inorganic compounds and producing organic ones. And therefore, these organic substances were necessarily connected to, to the to the living organisms or in clear connection with life. However, there was a scientist called Friedrich Wöhler, who was a German scientist, who in 1828 was able to produce urea from ammonium cyanate. At his time, ammonium cyanate was not classified as an organic compound, but more related to inorganic world, let's say. So his synthesis of urea from ammonium cyanate, it was like a clear mm, evidence that this notion of vitalism, which was adopted by great scientists of the time like Berzelius or Stalin himself, and you should remember Stahl because of the phlogiston theory. So Wöhler results clearly contradict this statement about the necessity of a vital force or a mysticism around the production of organic compounds. And with his experiments that he could reproduce, he showed that he could obtain urea, which was a clearly organic substance because it's derived even in the urine of animals and so on. It could be produced by what they thought to be an inorganic compound. For us today, it would not necessarily be the case because we still can define ammonium cyanate like an organic substance, and the experiment itself is not that impressive for the knowledge today. However, his contribution is considered significant because with this, what he did is a motivation for other chemists to try to synthesize organic compounds and destroy this mysticism about vitalism and the necessity of of a vital force, which was at the time thought to be not possible to do by chemist people. So it was thought that a chemist could modify some, let's say, chemical composition of matter, but they cannot manipulate or could not manipulate the vital force. Therefore, there was a barrier, or at least a psychological barrier, that chemists at the time were not able to produce organic substances, which Wöhler demonstrated is not true. And then chemists could do that. And because because of this new perception, one of the students of Wöhler, who was called Adolf Wilhelm Hermann Kolbe, he was able to synthesize acetic acid. And he did in a way that there was a very clear uh, synthesis or mechanism in which he was able to demonstrate that acetic acid, which is a compound, an organic compound, is possible to produce it from inorganic compounds, from carbon, hydrogen, and oxygen. So this was the final evidence that in fact it was not necessary this vital force, but it was just the necessity of special procedures to be able to synthesize these organic matters or compounds. Further, a little later, there was a French chemist called Pierre-Eugène Marcellin Berthelot, who during 1850s he was already in the position of doing organic synthesis in series. basically. So he was able to report the synthesis of compounds like methyl alcohol, ethyl alcohol, methane, benzene, and acetylene, which at the end of these demonstrations, the clear evidence is that vitalism was not the case and that organic chemistry was an expanding field of chemistry. Despite the success of Berthelot and Wöhler and Kolbe on the synthesis of small organic compounds, we have to say also that one main difference between inorganic and organic compounds is the size of the molecules. And the inorganic compounds are typically consisting of around 10 or less than 10 atoms. However, organic compounds they can extend to hundreds or even millions of atoms per molecule. Therefore, the achievement of Berthelot and so on, it was successful, but uh, not necessarily uh, representative for the complexity of the molecules or compounds produced by living organisms. These compounds that are more representative for the living world are typically uh, much larger molecules, like in the case of fats or proteins. And the synthesis of such a large molecules was still not possible for the chemists at the beginning of the 19th century or the 18th century. One important contribution on that respect was done by a German-born but Russian, he considered himself like a Russian chemist called Kirchhoff, who was able to produce sugar or glucose from starch by heating the material with sulfuric acid. Uh, the method itself is described like the mixture of 1.5 pounds of sulfuric acid in 400 parts of water to 100 pounds of starch. The reaction was carried out during 24 hours at 90 to 100 degrees C. And what is important about this reaction is that at the end, the reaction did not consume the sulfuric acid. Therefore, it was required to apply a specific amount of chalk to neutralize the acid. And later, it was termed by Berzelius that this type of reactions where for example, in this case, the acid is not consumed but is required for the reaction, it is called catalysis. And this was termed by Berzelius like that. So this reaction by Kirchhoff, it was one of the first, or maybe the first example of catalysis. Other contributions by Kirchhoff were, for example, in fermentation, in wet process to produce cinnabar, and refining of heavy earth or baryt, among others. Another important development was achieved by a French chemist called Henri Braconnot, who was able um, to isolate glycine, which is it was which is called like an amino acid by Berzelius because it has an acid group and an amino group or the nitrogen group. So Henry Braconnot was the first to be able to produce this glycine, and later after him there was attempts to produce other 20 amino acids, and all of them were isolated from occurring proteins, and the process were achieved during the next century. two more things to highlight in this slide is that Henry Braconnot used a similar approach to the isolation of glycine, like it was shown by Kirchhoff. So he also treated the compounds with an acid or a base at a slightly high temperature in order to isolate the glycine. And the second thing to highlight is that even though I'm showing in the slide some molecular structures as drawn today, for the chemists at this time, it was still not achieved. So the most they could do is to give an approximation of the uh, composition, so empirical composition of the compounds, but they were not able to represent, or they still was not developed the representation of the structural formula like we see on this slide. So it is here shown just for informative purposes. The next important step in the synthesis of organic compounds was taken by Michel Eugene Chevreul, who, during his scientific work, he was focused on the study of fats, and he found that, or he could isolate fatty acids from soap for the first time when treating these soaps with acids, again like in the protocol developed by Kirchhoff. And what he could isolate was fatty acids, but he also demonstrated that during the conversion of fats to soap, glycerol was removed. And this was an important achievement because later it was Pierre Marcelin Berthelot again who made another contribution on which he was able to synthesize tristearine by heating stearic acid, which is a fatty acid, with glycerol. So he took the fatty acids, which were isolated by Eugene Chevreul, and produced a fat, a natural occurring fat, which is called triasterine. So he was able to reproduce a much more complex molecule. In fact, it was the most complex molecule synthesized at his time. And the properties of the product, they were exactly the same like the natural occurring fat, the triasterine. With his contribution, then the Vitalis became totally obsolete. And Berthelot, he took the steps even further because he started to produce fats that were not occurring naturally. So in the first case, he used stearic acid, which is a naturally occurring compound, a fatty acid, and he was able to produce a fat which occurs in nature. But later, he started to produce other fats with acids that were not necessarily from organic or natural origin. And by doing so, he was able to produce organic compounds in the sense that they contain mainly carbon and hydrogen, but these new fats, they were not occurring naturally, or they were not produced by living organisms. In this sense, then the definition of vitalism became obsolete because with his products, he showed that it was possible to produce organic compounds without the need of a vital force or the process of a living organism. From this point on, a clear division between inorganic and organic chemistry can be traced or can be seen because, as we know already, organic molecules contain dozens to millions of atoms, while the inorganic had typically less than a dozen. And nowadays, also, there are very clear differences, and since his time, the differences in techniques, because as we discussed already, the organic molecules are much more sensitive, and this can be explained also by this huge arrangements of atoms that they can be much more easily broken and they cannot recover to the original compound like it could happen, for example, with inorganic compounds. And another important difference is that while inorganic, like for inorganic chemistry, the empirical formulas were enough to identify the compounds, it was not the case for the organic compounds because there are other situations like the case, for example, of isomerism, where the empirical formula is not enough to identify a molecule, and we will talk about it a bit later. In previous sessions, we were discussing about the importance it had, the quantitative measurements for the development of chemistry. And we saw that it started with gases, there's all this quantitative analysis, and the person who was like the key person for the development of this quantitative measurement was Antoine Lavoisier. And we know that he also tried to determine the carbon and hydrogen proportions of organic compounds by burning them. And after the combustion, he tried to measure the CO2 and water produced after the reduction, after the combustion, and therefore trying to determine the empirical formula of organic compounds. However, we know that his results were not sensitive enough, were not precise enough, and it was needed the contributions of Gay-Lussac and Jacques Thenard. Uh, we should remember that Gay-Lussac made his contribution about the law of combining volumes, and this was useful for the determination of uh, the proportions when they try to mix different gases and how, and also to the discovery or yeah, to to demonstrate the diatomic nature of some gases like hydrogen or oxygen, so nitrogen and so on. So with these achievements of Gay-Lussac and the contributions of Thenard, they were able to improve the precision of the data achieved by Lavoisier. And they did so by adding an oxidizing agent to the combustion reaction. And in this way, they could achieve a much more complete combustion, and therefore they improved the precision of the data. Another relevant contribution was done by a French chemist called Jean-Baptiste André Dumas, who complemented the method, and not only carbon and hydrogen, but also nitrogen could be achieved in his method. He is important because he discovered or developed what is known like the Dumas method, which has some advantages to other methods that we still use today. So even Dumas method developed in 1826 is used today because it has some advantages over, for example, the Keldal method because it is much more easy and is fully automatable, and the results can take just a few minutes for the determination of nitrogen. So this was like a time line for the development of organic analysis, and it's still improving until today. However, it was soon discovered that the empirical formulas, even in the improved versions by Dumas and Gay-Lussac and colleagues, uh, they were not enough for the identification of compounds, and this was clear by coincidence when two different chemists working with one of them working with silver fulminate and another with silver cyanate sent a report for a publication to a journal which was edited by Gay-Lussac. So Gay-Lussac, as editor, he received two independent reports with two different compounds with different properties, but with the same empirical formula. After he received this and he realized this situation, he asked for advice he showed these results to Berzelius, who was the greatest chemist at the time. And it is said that Berzelius was skeptic about the validity of these results. However, Berzelius himself, he was able to discover that racemic acid and tartaric acid seem to have the same empirical formula. And after his own discovery, he gave the name of isomers to such a type of compounds. So from this we can see that in the case of organic chemistry and the characteristic of these molecules of containing such a large amount of atoms, and that the atoms are mainly carbon, hydrogen, and nitrogen, then there is a place or an opportunity for producing molecules with different arrangements that have the same empirical formula but different properties. And this is the situation with isomers. Another interesting achievement and experimental achievement was done by Louis Pasteur in 1850, who was able to isolate or to separate the two isomers or worked by Berzelius, but for doing that, he first crystallized them like ammonium tartarate, and he was able to separate the isomers by a tweezer. So by hand, he was able to check what is the orientation of the small crystals which he formed. Even by naked eye, you can do it. And he just picked them up one by one according to the crystal orientation. And this is important because uh, with this simple experiment, he was able to prove that uh, isomers, despite having the same empirical formula, they differ in the symmetry. So the conclusion was that isomerism is the result of a symmetry, and we will talk about it a bit later. But in order to analyze the symmetry of an organic compound, you will need to see the structure. And at the time, it was still not developed the method or the idea about how to represent a molecule as we know it today. And even more, if you think about a molecule like a fat or like a protein that have lots of atoms, it was not it seems to be like an impossible task to represent how many isomers could be there. If you think that the position of hydrogen or carbon, it could be changed in several positions that they could not represent. So the task of solving the molecular structure, it seemed to be simply just an impossible. However, some advances were taken by Gay-Lussac and Thenard, and later by Wöhler and Liebig, where they demonstrated that even though it was unknown the structure and about the position or the arrangement of atoms in the molecule, there seemed to exist some what they call like radicals. And for example, in the case of Gay-Lussac and Thenard, they demonstrated that cyanide group it could be shifted between molecules without breaking the carbon-nitrogen bond. And even more, it is so because the cyanide group, it behaves very much like chlorine or bromine. And therefore, when you want to arrange or you want to place it into the molecule, you should consider like a root. So, yeah, so that's why the name of radical. Something similar, it was demonstrated by Wöhler and Liebig, where they showed that the benzoyl group, it can be switched from one molecule to another without being disrupted. This idea of radicals was adopted by Berzelius, and he even put it a bit farther, and he said that it could be explained, or that these radicals exist so strongly attached because of the electrical forces that attract these atoms together. And for that, he required to differentiate between atoms of positive charge and atoms of negative charge. And for example, some negative atoms will be carbon, chlorine, etc. And other positive examples will be the case of hydrogen. And therefore, the carbon-hydrogen bond, for example, is explained by electrical force that the negative carbon is attracted to the positive hydrogen. And this idea of electrical forces also comes with the idea that atoms of the same charge cannot be bound together. So it wouldn't be possible to make a carbon-chlorine bond under this theory which was held by Berzelius. And remember again that he was the most influential chemist of his time. And therefore, when one of Dumas' students called Auguste Laurent demonstrated that he was able to replace hydrogen by chlorine in some alcohols, for example, then Berzelius became very stubborn and rejected these results from Auguste Laurent. And to the sad part of this story is that Dumas, who was the teacher of Auguste Laurent, he supported Berzelius' point of view, and let's say that uh, how to say, he mistreated, or he didn't believe in the results and the evidence shown by Laurent, even though he was able to go further and to achieve an account for more and more evidence of these substitutions. And this was a clear evidence against the beliefs of Berzelius, not only in the concept of radicals, where Laurent was trying to break these radicals, but also in the possibility, or better, in the impossible bond between carbon and chlorine that Laurent himself, he proved that it was not true, and it could be done. And even it could be done without changing dramatically the properties of the compound, because Berzelius, when he saw these results, he claimed that if there is the possibility of this type of bonds, then the properties of the compounds must be completely different, which was not the case again. And that's why also there was like a conflict between Berzelius and Auguste Laurent. After Berzelius' death, the work of Auguste Laurent was highly received or appreciated by the chemists of the time. And more clearly then, from that point, Auguste Laurent rejected some of the principles developed by Berzelius regarding, for example, the electrical forces, and he adopted what is known like the theory of types, or he developed this theory on which all the molecules of one type are built around a nucleus, an identical nucleus, And around this nucleus, you could attach different types of radicals. For example, in the figure to the right, below the image of Laurent, you find what is defined like the water type, on which you have on the top the water molecule. But if you replace one of the hydrogens by a methyl group, then you will have methanol. Or if you replace both hydrogen, then you will have ethers. And what is interesting is that some of these compounds, for example, in the case of alcohols, they resemble very much of the properties of the water itself. Like, for example, they can react in some similar ways. The solubility is high between them and properties like that. Later, there was or around the same time, there was a chemist, a French chemist called Charles Adolphe Wurtz, who extended this. He adopted the theory of types, but he also showed that it's not something just related with, let's say, oxygen or water, but it can be extended also for nitrogen. And then he was working with ammonia, and he showed that in the case of ammonia, a nitrogen atom is bound to three hydrogens. But if you replace, for example, and you produce amines, then you replace some hydrogen with organic radicals, and they resemble this a type of another type which can be called like ammonia type or with a nitrogen nucleus. However, despite the advance of Auguste Laurent, the basic question of the molecular structure was avoided because there was not a clear representation of the arrangements of atoms inside the structure. It was just the notion that how the atoms can relate or bound to each other. During this period, around the 19th century, there was compendiums of organic compounds that were published or arranged based on this theory of types. But as we will see, it still was not clear how is the representation. So for example, these figures that we see below the image of Auguste Laurent, they were not produced yet. It was a representation that was produced after or later. And we will talk about it next. So with the development of the theory of types, uh, not so much time after that, it was found that the nucleus of the molecules, and here we should remember that still at this time there was no evidence of a nucleus in the atom. So this is the nucleus of the molecule. So when we talk about the theory of types and we refer to the word nucleus, we are talking about these atoms, which are the center of the molecule where other radicals are attached. And we are not talking about the nucleus as we know today, made of neutrons and protons. So with the list of organic compounds organized in order to explain the theory of types, soon they found that some of the elements they always combine with a fixed amount of radicals or atoms. Like for example, oxygen always combines with two other atoms or radicals. Similarly, nitrogen always combines with three atoms or radicals, and so on. So they could see that even some metals, they have some fixed number of atoms or radicals that they can combine. And it was Edward Franklin who was working with organometallic compounds that developed what is known like the theory of valence. And he listed what is the power or the valence of each atom and how many radicals it can combine. So this is another advance to the development of the electronic structure, still not there, but is getting closer. And this theory of valence was also useful to understand like electrochemical principles. And then you should remember about the Faraday's laws for electrochemistry. And yeah, so it was useful to differentiate between equivalent weight and atomic weight, because the equivalent weight then would be the atomic weight divided by its valence, and the valence refers to the number of possible combinations of an atom or a nucleus in the concept of the theory of types. Next, to the development of the structural formulas, then there was a Scottish scientist called Archibald Scott Cooper who proposed to use dashes lines to represent organic molecules, and it was rapidly accepted as it was useful to explain phenomena like isomerism, and also to explain double and triple bonds and to represent valence. In the field of organic chemistry, it was Auguste Kekulé who made great contributions to the development of structural formulas. So he took the valence theory and this new representation method by Cooper and show the electronic structure and the structural formulas for some simple organic compounds like methane or acetic acid, ethyl alcohol, and dimethyl ether. With this, he showed also that the molecules can grow almost at pleasure, because unless if you keep the valence rule, you could just attach oxygen atoms or carbon atoms and grow long chains like it was expected for, let's say, fatty acids or for proteins or whatever. There was also an interesting story about his idea for representing the molecule of benzene, because if you see in the image to the bottom right, all these molecules are linear, but there was still an idea or a question about how to represent benzene, because the properties uh, that were measured for this compound could not be explained by the geometries of a linear compound. And he said that once he was riding a bus and he was falling asleep in the bus, and he got this idea of kids playing, like holding their hands, or like monkeys and holding their hands and legs, like in the picture, and they formed this circle. And then he said that in that moment he realized that this could be the reason or the structure that could explain the phenomena or the properties of benzene. And then he drew for the first time the cycles, the cyclic benzene molecule. Despite the great contribution of these structures drawn by Kekule, still there was no clear explanation about the optical isomerism. And for understanding this process, we should discuss about a common or a collaborative work between physics and chemistry. More precisely, the work developed by a French physicist called Jean-Baptiste Biot, who analyzed or who was doing experimentation with polarized light, and he realized that when this type of light is passed through certain crystals, then the plane at which the waves undulate is rotated. And sometimes this rotation of the plane of the light, it is shifted clockwise, and sometimes it's counterclockwise. And from that point, he started to test different crystals, and he saw that even some sugars could make this process of the rotation of the light. Among those crystals, he found that the racemic acid and tartaric acid, which were the isomers discovered by Berzelius, they had this property, and despite they have the same empirical formula, the only difference they show or they exhibit was the optical properties. So one was shifting the light in a counterclockwise direction, and the others in the clockwise direction. And remember that also these isomers could be separated by Pasteur, as we discussed previously, and it was deduced that this is caused by symmetry. But if you analyze the way how the uh, structures of the molecules were drawn at the time by Kekulé, you still could not realize that where is the asymmetrical point. And for that, we will need a three-dimensional representation of the molecules, of the molecular structure. We need the 3D representation because it was soon discovered that the asymmetry is not just in the crystal, in the macroscopic crystal that you could crystallize and then you can separate, but also this optical activity, it was detected in solution. So not only coming from the crystal growth, but is an intrinsic property of the molecule, and therefore this asymmetry eh, it should be present also at the molecular level, not only at the crystal level, which can be millimeters or larger size. The next major contribution for the representation of molecular structures was taken or given by Jacobs Hendrikus van Hoff. And this is somehow inspiring because he suggested that the four bonds of the carbon were distributed in a three-dimensional space in a tetrahedron shape. And he did this suggestion during his PhD studies. So he was not graduated yet, but he suggested that the distribution of the radicals and how he's bound into the carbon, it should be represented in a three-dimensional space. Uh, this contribution is sometimes called like the Van Hoff-Lebel theory because it was at the same period of time, or this contribution was also simultaneously presented by a French chemist called Joseph Achille Lebel. And this was important because it could explain optical isomerism about how it is the rotation of these radicals in reference to the carbon, but also it could explain other concepts like the stability of the organic compounds. And for that stability, it was Johann Friedrich von Weyer who developed what is known like the strain theory. And he is based on the concept that the natural angle, as he called it, between carbon atoms that are stable is 109.5 degrees. But if this angle is strained by the geometry of the compound which is formed, then the stability is affected. Like for example, in a 3-carbon ring, the angle between the carbon atoms is only 60 degrees. And that could be the reason, or this strain in the carbon-carbon ring, this strain is the responsible for the instability of the compound. And that's why it is less stable than let's say, a 4-member ring or a 5-member ring, where in the 5-member ring is the most stable, while the others, which is beyond this, is getting farther away than this ideal angle or the natural angle of 109.5 degrees. This theory of 3 dimensions was not only discussed for the case of carbon, but also for other elements or other atoms. Like for example, Victor Mayer also did some 3D representations for nitrogen, William Jackson Pope for sulfur, selenium, and tin, and Alfred Werner for cobalt, chromium, rhodium, and other metals. Also, Alfred Werner is recognized because of his contribution for complexes. So that the interaction between, let's say, a central atom and the radicals is not only explained by the valence, but also about dative covalent bonds and so on. Another important conclusion from this 3D representation is the understanding of the steric hindrance. So this is important in organic chemistry because it can show how is the mechanism, or can explain the mechanism of why reaction happens in certain points and why is hidden from other points. So there is this steric effect which is hidden or hiding some reactive centers, and therefore it could explain process in organic chemistry, let's say. So this was the material for today, and during the next week we will talk about physical chemistry and a little bit also about the periodic table. So thank you so much.